Welcome back, everybody. So we are now going to continue. First with the fix, because I figured out what happened. I was horrified when I saw that Alexa was not on the slide. I actually, there was a TA from another course that I swapped him with. So this is now the correct slides of the TAs. So maybe a big applause for the TAs who are going to encourage you the whole semester. And for getting Alexa on the slides, have a bit. You want this? Which one?
Oh, thank you very much.
This one? All right. And of course, I'm not forgetting Marcin. There you go. Okay, so now that this is correct, I'm going to continue with data independence. So I warned you, this is going to be all over the place the whole semester. I'm going to keep saying data indie, wait for it, pendants, right? So the whole way data independence the whole semester. You need to understand this one thing. The idea is that we have two levels, a logical level and a physical level. The user, you, in the end, should only ever have to deal with tables, the logical data model. You look at tables, you see tables, you query tables, you get the results of tables, you interact with tables, you dream at night about tables. This is the logical data model. And then some people implement it so that it works on computers with physical storage. It's going to be stored on disk as files and so on. But as the end user, you don't see any of this. This is data independence. And the reason it's powerful is that then you can swap things. You can, in fact, use a clay tablet instead of a computer. It also works. It's a bit slower, and people actually were doing it this way before. But the model is the same. You still have a table with columns and rows. You could have a data center behind this. This is what we do in Big Data for Engineers. We had a whole cluster of machines where this is executed. But again, the students who took Big Data for Engineers, maybe you remember that we were also using SQL in order to query the data in there, Spark SQL. And there are even people who do it on DNA. Thomas Heinis is one of my former colleagues at ETH. He's now at Imperial College, a professor. They succeeded at storing relational data in DNA and querying it with SQL on DNA. So it's another beautiful example of data independence because the model stays the same. So this is the reason why in this course we are going to focus a lot on that logical model, the math of the relational model, the rows, the columns, the attributes, and how to query it, because all the rest just happens automatically. So that's the spirit of data independence. Now it's a whole ecosystem, the database world, because since there are these companies like Oracle, IBM, Microsoft, SAP, and all the open source PostgreSQL, MySQL, and so on, then of course that creates jobs, that creates positions. And so what kind of jobs are people doing in the companies? Well, they are the sysadmins who are installing the database, maintaining it, making sure that everything is correct. They might manage the access control, the accounts, making sure that people have access to the things they should have access to. They will monitor that it's backed up, that everything is working properly, coordinate, and so on. So these are the database administrators. Then we have people who are specialists of the logical model for creating schemas. They know all the theory and the math of the higher normal forms that we'll study in a few weeks and so on. Can become very complex. I'll show you some of that. And so they know how to design schemas that are very efficient and make it so fast that when you are on your website, it appears in 2 milliseconds. Then there are the power users, the programmers that you might have heard of full stack developers on social media. Who is a full stack developer? Nobody? Okay. So these are the people who are writing programs. They know how to write SQL. They know how to write Java, C++, JavaScript, PHP, and so on. And so they're able to build a whole website connected to the database and so on. Right. So programmers, power users. Then we have the data scientists, the data analysts. So they have a bunch of data that they're supposed to analyze, and they have to produce visuals. So they know how to write SQL queries and how to update the data. And so they're sitting typically in front of their computer, maybe using a Jupyter notebook, and they're typing queries and seeing the results live, and they're preparing a report for their managers, right? So these are the data analysts. And then we have parametric users that do not necessarily know SQL. They don't know how to program, but they have some user interface on their computer that they can access the database with. This is very commonly what you would have in call centers. You know, when you're calling the customer service of a company or the technical support, these people are not entering SQL queries in real time. They're connecting to the system with forms, and they have text boxes, buttons. They can enter parameter, click search. So this is a more interactive way of using a database, but this is, again, a relational database. Who heard of Microsoft Access? Right? That's exactly this kind of technology that allows you to access it without any SQL knowledge. So you see there's something for everybody in here. Okay, and now still on the high level, because of course we'll have the whole semester to explore. What is a database system made of? So there is one distinction that needs to be made for the rest of the semester that you know between metadata and data. What we call metadata is here the headers, for example. That's part of the metadata. Meta means about something. It's about the data. Metaphysics, about physics. Meta-mathematics, actually, you're doing meta-mathematics and not mathematics when you write an exam on mathematics. So it's about the data. So these are the names of the headers. The types, so for example, saying that this is an integer, this is a string, these are numbers, this is all metadata. And the data itself is this. That's what you have in the actual cells. So if you use spreadsheet software, you probably noticed that the first row is a bit special, that it's formatted differently and put differently. This is because it's the metadata. What does it mean for the system? Well, it means that it has to manage both the data and the metadata. And so it's pretty, on the very high level, it's actually pretty simple, because where is the data? Well, it's on disk. It's the zeros and ones that are stored on the mechanical drives, right here. Then you have the user, that is the data analyst in their Jupyter notebook. What they are doing, the fancy word for that is data manipulation language. All that means is they enter a query. That's what it means, right? But we call it DML, data manipulation language. And in the middle, that's the piece of software that you download it, free and open source if it's PostgreSQL, and then just interact, not directly with the disk, but going through PostgreSQL, the data manager, you interact with the data. So that's for the data. The metadata is the same thing almost. I just swapped a few words here. The metadata is obviously also stored to disk, because you also don't want to lose that, right? There's a metadata manager, that's again PostgreSQL in the course. And then here is the data definition language. What's the difference? In the data manipulation language, you might say, give me all the cities of Switzerland that have between 2,000 and 5,000 inhabitants. That's data manipulation language. Or please insert into the database this person. That's data manipulation. Data definition language would be, I want to create a new table to store people, and I want it to have this column, that column, this column, that column. That's data definition language. Or I want to add a new column to that table for storing something else. That's data definition language. All right, you see the difference? Data manipulation, that's about the data. Data definition, that's about the metadata. All right, and if you put it all together, then you get this, right? So the whole database system, data, metadata, that's the database. In the middle, metadata manager, transaction manager, that's PostgreSQL. Transactions, we look at them in a couple of weeks. This is the reason why you can have thousands of people booking a flight or a train at the same time. That's the transaction manager. It's making sure that things do not go wrong when plenty of people use the system. And DDL, DML, remember, DML is data manipulation language, DDL is data definition language. We'll see it's actually SQL. DDL and DML, it's all SQL, the language we'll learn. Everybody still following? So now, what's important is that the metadata is going to be just put once, typically, and you can still modify it later. But what is going to change is the data. Imagine you're a store on the internet selling things. You have millions of people every day on your website that keep buying things, so the inventory keeps changing. There's new customers creating accounts. So the data has its life. The data just changes under the constraint of the metadata, right? So you might add new records, you might modify values, but this usually stays more or less. You can change it, but it's not going to be something you do often. Right? That's just once in a while. So there is a life cycle, and there is a whole life about the data. Okay. Then I'm going to say a few words. Actually, it's almost the end of the introduction. A few words about query languages, but we'll spend several weeks on them. So again, we'll go into details of that. What do you need to know about languages? The first thing you need to know is that there's two kinds of languages. There's what we call the imperative languages, and there's what we call the declarative languages. You can compare it to cooking. If you are at home and you go to the grocery store and buy the ingredients, and then you have a recipe book, and then you do everything that's in the book, that is an imperative language, what you find in the recipe book, right? You do everything yourself, and you have all the instructions to go through it. A declarative language means you go to the Polymensa and you ask for the veggie menu. That is declarative. It does the same thing because in the end you get food, but the way you do it is not the same, right? And of course, when you have a declarative language, there's often hidden an imperative language, because of course, if you go to the Mensa, the veggie menu doesn't just pop up out of nowhere, right? There are people who actually do the cooking, but you have this separation of tasks. And so it's the same thing here, that when you have languages like Python, Java, C, C++, you give instructions to the computer. You tell the computer, do this and do that and do this and do that. That's an imperative language. But the beauty of a language like SQL that we will study is that it's declarative. You don't need to tell the computer how it should do its job. All you tell the computer is, this is what I want. For example, when you say, give me the cities of Switzerland that have between 2,000 and 5,000 inhabitants, that's declarative. You just say what you want. The details of how it's done, you don't need to worry. Somebody could do it, of course, in Python or in C++, but you don't need to worry about it if you're using SQL. You just declare what you want. And so that means that typically when you have a website like this, you have the layer of SQL. So that's the data analyst that uses that language. Then PostgreSQL, of course, has to be implemented in some language, right? And typically it's going C++, going to be C++, Java, languages like that, right? I don't know which one they actually use, but it's an imperative language. But these people don't need to worry about this one. It's all hidden. You just download it. And then the physical layer, and now we've almost forgotten about it because it's become so obvious, but in fact, there's the CPUs, the processors, the chips, the electronic components, and so on. And here we even have assembly codes that is the lowest ever that you can go to. And now most computer scientists cannot write assembly code anymore. That's really something that very highly specialized people would ever do, right? Because we can compile C++ or Java to assembly code. All right, so these are the layers. And of course, here we're going to focus on SQL. What does it mean that it's declarative? Well, hello, data independence. Again, we have a logical model in which we think when we write the language, the declarative language, and that's going to be physically executed. And that's where it writes on the disk and reads on the disk. And so there's again that distinction between the logical level and the physical level. So having a declarative language is very tightly tied to the idea of data independence, right? So typically what's going to happen, it's a very complex piece of software. What PostgreSQL is going to be doing is that it's going to look at your query, analyze it, and think, how am I going to execute that? And then it comes up with a few plans. Maybe I could do it like this, maybe I could do it like that. Then it's going to estimate the cost. If I do it like this, it's going to take 10 seconds. If I'm going to do it like this, it's going to take 20 seconds. And then it picks a choice. 10 is better than 20, so I'm going to go that route. And then you go ahead and execute it. But all of that is hidden. You don't see any of that. You just press enter after you input your query, and then you see the results. So this is called the query plan, when the engine is trying to figure out strategies to implement what you want. That's called the query plan. And of course, that's the same idea of swapping the computer with a data center, a clay tablet, DNA, and so on. We can also swap the execution, because that can be on a single machine. That can be also in parallel on 10,000 machines, right? That's what we do again in big data for engineers, right? So the beauty of SQL is you learn it just once, and then it's exactly the same language, whereas it's whether it's on your laptop, in a data center, it's still the same language. So I'm going to ask at the end of every one of the lectures, making sure that you're following me. The goal of that question is a bit like a remote control. So you can accelerate me or slow me down. Because if I see that everybody says I understood everything, then maybe I'm going to accelerate a little bit. Then if I see that many people start saying, no, I understood less than half and so on, then I'm going to slow down, right? I'm going to adapt to you. So now maybe today is just the introduction, so maybe that makes a bit less sense, but I'll just do it regularly to make sure that I'm not leaving anybody behind. And then, of course, outside the lecture, you can send questions to the Moodle forum. You can write to the chat. You can send me an email. You can send the TAs an email. You should not be afraid of asking any question. Right? That's what we are here for, and we just want to make sure that you're following. Right. So now it's al dente. That's exactly about right. By the way, so there's no exercise sessions this week. They start next week. You will notice that one of the exercise sessions is marked as a focus group. Who heard of focus groups? That's the Fawe CTH initiative. So for those of you who might have a bit less of a mathematical background, because there are so many departments that you have different backgrounds. So if some of you feel that they are a bit hesitant or not very confident about math or about the technical side, then come to the focus group. And the TA then it will specifically offer the exercise in a style to take the time to answer questions, go into the details of the concepts and so on. Right? So you have this possibility. In addition, of course, to asking all the questions you want to us about the material. Okay, so any questions? Yes? The execution of multiple queries at the same time. So parallelism is the idea that you execute one query, you still have looking at one query, but you manage to find the strategy so that you can use thousands of machines for this query. I'm going to give you an example, a naive example, because that can be done better than that. Imagine that you have a database with everybody on the planet, right? 8 billion people. So it's a table and there's 8 billion rows. And now it's so much information, actually it fits on your laptop, sorry, but imagine it doesn't. So you just spread it over machines, right? Because it's so much data. So let's say you spread it over 1,000 machines, and every machine has information. If it's 100 machines, that should be 80 million people per machine, right? So you have 80 million people on every machine. And now the query is this. You're looking for somebody. You're looking for Albert Einstein. So you're looking for that for one person. Do you see that since the data is spread over the machines, what you can do as a strategy for executing the query is that each machine looks on its own drive if the person is there. What's going to happen is that most machines are going to tell you, no, I didn't find this person. And one of them is going to tell you, yes, I found that person. Do you see that doing it in this way, in parallel on 1,000 machines that all search on their own part of the data, is going to be faster than having all people on the same machine and only that machine is searching through it? Do you see it's going to be 1,000 times faster? Do you see that? Yeah, that is parallelism. Of course, it's a bit more complex than this. It's extremely powerful what you can do with parallelism, but it is the idea, you can see it a bit as cheating, right? So you have your query and you cheat by using 1,000 machines instead of just one. So this is parallelism. All right, but we are not going to look at parallelism in this lecture. I'm telling you it exists, but this is something we do in big data for engineers. Any other questions?